Hi, I'm NG, and today I will talk about the topic transition of municipal wastewater treatment plants to waste resource recovery facilities. Okay, so traditionally, the goal of wastewater treatment was to protect downstream users from health risks, and all contaminants were removed from water before discharging to the bodies of water again. And in more recent decades, protecting nature by preventing nutrient pollution in surface waters has become a new approach. And consequently, nitrogen and phosphorus removal technologies have been, implemented into wastewater treatment plants. The most used wastewater treatment method is conventional activated sludge process, which aerobic microorganisms is used to metabolize organic compounds with the presence of oxygen. And this process is unsustainable due to low resource recovery potential and its high energy demand and large environmental footprint on other processes. On the other hand, in terms of natural resources such as fresh water, you may know apatite rock, which is the raw material for phosphorus production, it is known that these sources are running out. And all these steps raise awareness about sustainable development, including more circular use of resources, and the resource inefficiency of current wastewater treatment practices have driven research and development of new technologies to recover as much as possible the materials as well as energy in wastewater. Okay, so as you can see in the table, this is kind of the resource demand in Netherlands and Flanders, which is water, energy, nitrogen, and phosphorus demand. And in case of the water, as you can see, uh, theoretically, we can extract and recover around 50% of of water that can satisfy the demand in Netherlands. And it's also the same cases for energy, nitrogen, and phosphorus, which is really kind of impressive number. So I can say that nowadays wastewater is recognized as really high potential resources instead of just waste stream. So in the next part, I will talk about the innovative strategies for the water reuse, recycling of nutrients, and also energy generation. And about the water reuse, the definition is that this is kind of the method of recycling treated wastewater for beneficial purposes, such as agricultural and landscape irrigation, industrial processes, toilet flushing, and groundwater replenishing. About agricultural irrigation, you know that using reclaimed water to replace part of the agricultural demand can alleviate local water threats. And furthermore, nutrients contained in the wastewater can also reduce the fertilization application. And look at the picture, you can see that effluent from secondary treatment was recommended for irrigating non-food crops, vineyards, while effluent from tertiary treatment was recommended for food crop irrigation. Even though there are still some concerns about the quality of wastewater, which may cause soil pollution and crop contamination, and the high cost to construct pipeline from wastewater treatment plants to the land could also be considered. Uh, that about the industrial reuse, you know, there's some kind of the thermal power plant, the petroleum refineries, and chemical manufacturers. These kind of plants, you know, use significant amount of water, but I'm sorry, fortunately, they do not require water quality as high as for potable supply. So they are suitable candidates for the use of reclaimed water. And current industrial reuse mainly includes cooling water, boiler makeup, and industrial process water. The water from secondary treatments is also recommended to use for industrial cooling processes. And on the other hand, reclaimed water may cause problems such as corrosion, biological growth, and scaling compared with freshwater. Okay, so next part, which is the recycling of nutrients. Nutrient recycling recovers nutrients in the wastewater as fertilizers for beneficial uses. Nutrient can be recovered from wastewater sources, semi-treated wastewater streams, and treatment bioproducts such as biosolids. And recycling nutrient does not also means the save in depletion resources such as phosphorus or nitrogen, but it also consequently saving energy and water demand to produce fertilizers by these traditional processes. Okay, so yeah, as you can see, biosolids land applications involve spreading biosolids on the soil surface or incorporating or injecting biosolids into the soil. The advantages of biosolid land applications is that there isn't too much nutrient entering the soil due to the low content of nutrients in biosolids compared to synthetic fertilizers. Urine separations involves separation of urine from other wastewater sources for recovery of nutrients. And separating urine from wastewater can decrease the load, for treatment process. And the concentration of nutrient in the urine stream is rich, and it in turn is easily to recover nutrient by technology such as through precipitation. And in urine separation process, it should be considered because 70 to 80% of nitrogen and 50% of phosphorus in wastewater contains in urine. Even though the cost for applying this method is quite high, and it needs support from the local communities to apply this method. About the recovering nutrients through aquafiches means that to use the aqua species to utilize the nutrients in the wastewater and harvest and use the aqua species as fertilizers or animal feeds. The aqua species could be algae, wetlands plants, and crops, and so on. And the advantages of this method is that it can purify the wastewater as well as create energy for other processes. Okay, so the next I will talk about the on-site energy generation. The first one is combined heat and power systems. CHPs utilize biogas produced from an aerobic digestion to generate heat and electricity on site. The CHPs have an electricity generation potential of about 350 kilowatt hour per million gallons of wastewater treated. And biosolids incineration refers to recovering energy through biosolids combustion in fluidized beds or multiple health furnaces. And it doesn't only generate energy, but also reduces waste volume to the minimum, and thus cuts down disposal costs. The disadvantages of the biosolids incineration include, you know, definitely the release of persistent environmental pollutants, quality inconsistencies, the relatively high capital investment, and energy costs for dewatering the biosolids. And about electrochemical systems use biocatalysts for oxidation or reduction reactions for desired products. It includes microbiofuel cells system and electrolysis cell systems. MFC is a device, that directly converts microbial or enzyme catalytic energy into electricity by using conventional electrochemical technology. MFCs can also reduce the EC sludge to around 20% compared with the conventional treatment, thereby reducing the sludge disposal cost. And the last part of this one is quite interesting, which is effluent hydropower. And effluent hydropower is a technology that uses turbines or the device installed in conduits, pipelines, canals, so on, to generate electricity from effluent water. The effluent hydropower system can also increase the dissolved oxygen concentration in the treated wastewater. And the main constraint of this technology is that it requires the effluent to have sufficient kinetic energy to justify the investment. Hence, either the head or the flow rate must be significant in order to optimize the hydropower scheme. Okay, so in the final part of the presentation, we will talk about, I can say, the future wastewater treatment plan. And in this case, I choose this you can see here, this is the image of the process flow of hypothetical microbial fuel cells for wastewater plant. Firstly, you can see a settling tank or other primary treatment facilities, for example, batch screens, a debris basin, as in most of the existing wastewater treatment plants, can be adopted to remove the majority of, you know, the non-utilizable fractions, and meanwhile reduce the risk of the reactor clogging in the subsequent treatment step. And it depends on the wastewater properties. The wastewater can be treated via three different paths. You can see the first one, wastewater with a low organic loading can be directly fed into an MFC system. The secondly, high strength wastewater might need to be treated firstly in an anaerobic reactor for pre-fermentation before entering the MFC system. Then methane is heated to maintain the temperatures for an upflow anaerobic sludge blanket, which is the abbreviation of UASB. And the third one, phosphate-rich wastewater can undergo a strovite precipitation step for nutrient recovery prior to MFC treatment. In MFCs, the remaining organics are further exploited for energy production and possible recovery of a wide range of valuable products. The MFC treatment may be insufficient for lowering the aqueous nutrients to an acceptable level yet, especially for nutrient-rich wastewater like urine or soil wastewater. Therefore, the MFC effluent can be subjected to algae treatment for further improving the effluent quality and lifting the energy output, as well as environmental benefits from wastewater. And if you want to yield high quality water that meets the standard, membrane filtration processes such as ultrafiltration, nanofiltration, or reverse osmosis can be incorporated as a deep treatment step to further polish the water or even to further extract useful products from the effluent stream. Okay, so this is the end of my presentation. So once again, thank for listening.